cover until chapter 6 part 2, you need to do chapter 6 part 2. Okay, here. And this one is based on final exam. I think this is final exam question. Is it? Wait ah. Line slow ke apa ni? This one. Okay. You see, this is final exam. So try to do it. Okay. Okay. Now we go to the just a review of chapter 6 part 1, because I have been covered it in e-learning, I mean at YouTube. So please watch YouTube. Actually, you need to watch the YouTube first before this lecture, ideally. Okay, but I understand maybe you are busy, whatever, with your course, whatever, right? But try. Actually, you should watch before. Otherwise, you come to this session a bit blur because I'm just doing review. Okay, so go to chapter 6 part 1. Okay, this one. I provide the link, okay, for chapter 6 part 1 at e-learning. Either you guys miss it or you guys don't bother to watch, I'm not sure. But kenapa line slow sangat ni? Okay, so I put here. Wait dah. Jauhnya saya kena tekan bawah ni macam ni. Okay, this one, the link is here, because I provided it last week. Then here, okay, here, chapter 6 part 1, filter design. Okay, then today is just a review of it. We will finish at 1 p.m. X maximum. Okay. Okay. So chapter 6 part 1 is in this slide. I combine chapter 6 part 1 and part 2 so this will be covered 2 weeks of lecture. Okay, 2 weeks of lecture. So but we only cover part 1 for this 1 week lecture lah. Okay, this one is actually about Butterworth filters. Okay, until Butterworth. Okay, so there is actually a lot of type of filter response. Okay, if I was during my time, if I'm not mistaken, we study other type of filter as well. Okay, but maybe you guys lucky, it's become more simpler, so should be more easier. Not sure. So you only study Butterworth and Chebyshev. Okay, last time, if I'm not mistaken, I study base. I mean that protein, whatever. Okay, never mind. So you can see there is a lot of frequency response here, filter response. So you study here Butterworth and also Chebyshev. This is Chebyshev. If you see the lines here, and you have a ripple. Okay. So categories of filters, as you all know, is actually we have low pass filters, high pass filter, band pass filter, and band stop filters. Okay, the frequency here is actually the frequency at which there is a reduction of 1 over square root of 2 or 0.707 from the maximum. Okay, so that is your cutoff frequency. Okay. Same goes for band pass filter. We can assume is as a combination of either low pass or high pass. For this one, it looks like a combination of high pass filter and low pass filters. Okay, so but the cutoff frequency here is F1 here and F2 here. But the same, it is a reduction of 1 over square root of 2, where you actually map your cutoff frequency. So this is your band stop frequency. It looks like a combination of low pass filter and the high pass filter. Okay, the same F1, F2 is the cutoff frequency. Okay, where you actually obtain the reduction in magnitude of about 1 over square root of 2. Okay, or 0.707. Okay, this is definition. I think chapter 4 we study about filter. Chapter 4 is it? Which one? Chapter 5. Because I think it's like repeating. Yes, chapter 5 we study a bit about filters. Okay, so this is a filter response characteristic. So you have two kinds of filters. You have ideal filter and also practical. Okay, in ideal filter, your band pass is the gain is 1. macam perfect lah, gain dia 1. And then the band stop, directly we have gain of 0. So we don't have this kind of filter in real life. This one is ideal. Okay, because in ideal filter there is no transition band between this between band pass, between pass band and stop band. This one a bit confusing. This one is pass band and stop band. Band pass and band stop is a type of filter, but pass band and stop band is the band. Okay, so I think a bit confusing here. This one should be pass band and stop band. And then you have practical filter. This is the one that we have in real life. Okay, so we have a band pass, band stop. At band stop, the gain is not equals to 0 because there is transition not directly equals to 0. Okay, because there is no absolute in the practical filter. In the band pass, it can be any constant value in dB. Okay, and then because it's practical filter, so we have transition. Okay, we have transition between band pass and band stop. If you watch my video, I already shown what is the transition band. It's actually the in between of your stop band and your pass band. Okay, so this is the ideal response of filters. Okay, low pass filters. You have this green color is actually your ideal filters, and this one is actually your practical filters. We call this as non-ideal as well. So if we mention non-ideal, you should know what does it mean. Means it is a practical filter. Okay, just like Ras Hazika have many names. Sometimes people call her Ras, sometimes people call her Hazika, but it's the same thing. So you should know the non-ideal is actually practical. Okay, and then you have pass band and you have stop band. So pass band is actually the band where we actually allow the frequency to pass through, and stop band is actually where we attenuate or we block. But normally we cannot really block in real life. We can attenuate them. Okay. So this one is the high pass filters where we pass the high frequency which is greater than omega c. Okay. This one is actually similar, just a combination. Okay, once you understand low pass and high pass filter, this one shouldn't be a problem. Okay, you didn't know, you will not know whether you have problem or not unless you try the exercise. Okay, so try the exercise. So this is band stop filters. Okay, now we have two type of filter that we're going to study in this in your syllabus. Okay, we have two type of filter, which is Butterworth and Chebyshev. If you see from these two kind of graph, Butterworth shown by blue, Chebyshev shown by black. If you notice, Chebyshev have ripple. We have ripple here. Okay, so the ripple here is mx. Okay, the difference here is mx. And then if you see, even though Chebyshev have ripple, however, it have a faster roll off. Okay, faster roll off in such a way that it's much steeper. Okay, so if you see in terms of roll off, which one more better is that we can say it's Chebyshev because it more closer to ideal filter. Okay, in that sense. Okay, but however, Butterworth have slow roll off. Okay, but Butterworth have a flat gain here, flat pass band gain. So in terms of pass band gain, Butterworth is more towards the ideal filter because it's flat here, because Chebyshev is not flat. So maybe question, I don't know, question can be ask you many things, right? Maybe they will ask which one is better, which one is actually having better roll off, which one is actually more mimics, or I mean close to ideal. Depends, because depends on what kind of Butterworth you get. And then maybe your Butterworth here, for example, this one is maybe Butterworth an order of 9, and this one maybe Chebyshev order of 5. So end up maybe this one have faster roll off, because you need to see different case by case kind of question. Okay, but generally you have it like this. Okay, then this is the more I mean the further explanation on this Chebyshev. So you have this is your pass band, transition band, and stop band. Wait, okay, so you have this one is actually your pass band gain. Okay, pass band gain here, and this one is your stop band gain. Okay, so you can see this is omega p is actually the pass band frequency. Okay, omega, and this is cutoff frequency, and this one is a stop band frequency. Okay, so you can see a ripple, and the difference is actually your mx. Okay, so this is the filter design process generally. So you should know three main things first, which is the filter specs, find the transfer function hn, and here is actually normalized transfer function, and then after that you need to denormalize them, depends on the question, and then circuit realization. In Chebyshev, wait, I think Chebyshev you need to do circuit realization. Okay, okay, and then in filter specification, you have a type of response, whether it is Chebyshev or Butterworth, and then you need to know this cutoff frequency. Okay, whether you need to know or you need to find or it's given, but this one should be able to be, I mean, you should have this information. Okay, and then pass band frequency, pass band gain, alpha p, stop band, and stop band gain. This is the critical information that you should have or you should obtain or is be given, depends on the question. And then you will do your normalized transfer function. So polynomial, this one you learn from your mathematics course, either in matrix or in degree before coming to this class. And then circuit realization. So the filter response divided by two for this for our syllabus is Butterworth and Chebyshev. So you have Butterworth transfer function that will be covered in chapter 6 part 1. So you have this kind of transfer function, the normalized transfer function, and the Chebyshev, this is the normalized transfer function, and you have difference. If your n is even, this kind of question that you will have, and if it's odd, this kind of question that you will have. Okay, so this is the magnitude. Okay, penat saya sebab saya suruh cakap 2 jam. Sekejap saya dah tak boleh minum air ni. Okay, wait. So you see the filter response. This is Butterworth response. So you can see this is the plotting that you have. Okay, that I already explained. And this is the order of the filter. Okay, so order of filters. Okay, wait. Where is the appendix? So appendix for the chapter 6. Jangan tidur pula saya sebab saya seorang cakap ni saya sebut nama sekejap lagi. Okay, so wait. Okay, so here, okay, this is your chapter 6, Chebyshev, Butterworth, F, annual filter designs, table F1, and this one, and also this one, and also this one. So if this mentioned that order, so you see at your Butterworth filter, because this is Butterworth, so go to your Butterworth filter. Okay, then you see there is a coefficient of Butterworth polynomial. Okay, so n2 means order of 2, n3 order of 3. So as increasing, you will have more coefficients a, because a1, a2, a3, and until you n9, because we are using polynomial. Okay, polynomial shown here. Okay, so Sn plus An minus 1 plus Sn minus 1. So the next one is An minus 2, Sn minus 2, until you actually will end up with your 1. Okay. So as you can see, the greater the order, the steeper the curve. That's why I said just now, this one is generalized, general. But if, for example, if you have Butterworth order filter which is higher, it can be faster roll off. Maybe better than Chebyshev. But we need to see also the Chebyshev kind of order. So this is general, but you may have different kind of response or roll off decision or whatever that you can decide after you solve the question. Depends on the order and depends on the question. Okay. As you can see here, you can see order 2 is like this. As the order is increased, you have more steeper curve. More steeper curve means faster roll off. We call it roll off. Okay. So this is the order. You can see the trend. Okay. This one is what? Chebyshev. Okay. This one is Chebyshev. This one is Chebyshev. Have I already told just now the Chebyshev? So in terms of Butterworth versus the Chebyshev, so you can see in terms of passband, generally, Chebyshev have a ripple shown by the black. So you have ripple. For the Butterworth, flat. So we call it flat passband gain. And then roll off. For the Chebyshev, we have a faster roll off, means steeper curve, faster. And then the Butterworth slow roll off, means less steeper. Okay. Other names, I don't know whether it's in the slide or not. So we can call this Chebyshev is equal ripple filter, and Butterworth, if I not, we can also call it a flat passband gain filter. Okay. This one you only can get in record. If I don't record, maybe you don't remember. The previous section I told this, but I forget to record. Okay. So Chebyshev versus Butterworth. Okay. So Chebyshev, you have ripple at band pass. Butterworth, you have flat or no ripple. Okay. At band pass. And then Chebyshev, we have fast or better roll off. And Butterworth is steady state or slow roll off. Okay. So for the Chebyshev, even though it is a ripple, we have much more simpler circuit generation. However, for the Butterworth, it's a complex circuit generation. And then Chebyshev, we have known as equal ripple. Oh, okay. It's mentioned here. Okay. Okay. I thought I did. There's no in the slide. So Chebyshev is equal ripple, and Butterworth maximally flat, or you can call it flat passband. Okay. But many names. Maximally flat also can. Okay. But actually the other name just like flat. Flat filter, flat maximally flat passband gain filter. Okay. So we go to cover with chapter 6 part 1 with filter design for Butterworth only. Okay. For to design the Butterworth filter, the first step you actually need to know is actually you need to determine the first order number. This is the same as well for the Chebyshev filter, where you should be able to determine first the order of the filters. Okay, so means you can see from this equation when. So you should know the alpha S, you should know alpha P, and you should know you should know omega Sn. This one is the normalized omega Sn. Is it given here? Omega Sn? Okay, given. So omega Sn is actually the stop band cutoff frequency over omega P. You can see here. Okay. So after that, you need to calculate the value of omega C, which is maybe more than one, like this 2. Okay, you have 2. So you have omega C, which is dependent of alpha P here, and you have another omega C, which is dependent on alpha S. You will have two kinds of value of omega C, and you need to choose which omega C that fulfill the specification. So if you watch my video at YouTube chapter 6 part 1, you will understand because I do one question example. Okay. And then you need to determine the normalized transfer function Hn. Okay, refer at Butterworth coefficient. So you can actually from your appendix. Mana coefficient dia? Okay, Hn, where is it? Okay, this is the coefficient. So this is the coefficient of Butterworth polynomial. You see, Bn. So Hn is actually 1 over Bn. Okay, 1 over Bn. Bukan political party 1 over Bn here, Bn. So normalized. So it's a normalized transfer function. So because it is normalized, so it is not the actual. It's not the actual. You need to denormalize them. So how you denormalize them? you need to convert the normalized form by substituting. For example, if it's a low pass filter, okay, you need to change the S. If it's low pass filter and Butterworth frequency response, you need to substitute the S with S over omega C. Okay, this one is already explained in the chapter 6 part 1 video. Please watch. I'm not getting okay. The one of the reason one of the reason why I make this unlisted, one of the reason in the first place, first to protect my privacy, because something I may say wrongly because it's raw video. Second is that when I make unlisted like this, I will be able to see my student only view, because only my student have this link. So I can see, okay, up to now only 54. But if I make this public, means my number of view here not really reflected my student number anymore. Okay, so I make it unlisted. Maybe next week I will make it public for other section to watch, because I was informed by one of your friend, or maybe some friend of yours, that other student want to watch my YouTube video. I mean, yes, okay. I mean, they want to. It's okay. I can share later on, but not now, because my priority is my own student first. My own student not even watch it yet. How many not yet watch this? Uh, 12 students didn't watch it yet. Quite pity, 12. So I don't know what happened to you guys. Lecturer audio record. I record this at 2 during I'm sick, and it's 2:30 a.m. something time. I don't know. I already tried my best, okay? Now I left it to you. Just to watch. I don't know why is it so difficult to watch. Okay? Apa? Ani Sofia. Why you raise your hand or tertekan? I think you tertekan. Okay. Okay. Then I also explained in that video to do this Butterworth filter designs. Okay. And actually this is the parameter involved. Okay, I also explained, okay, in the video. Okay, if you get, for example, okay, please take note of this. If you mention here n, you when you obtain n, tekan tahu tekan. So n equals to 5.9. If you have n equals 5.9, your natural instinct, yang your mathematics skill will tell you to round to 6, right? But let's say if we have n equals to 5.1, what is the fifth order filter? Can you guys tell me? If you get 5.1 here, what is the filter order? Yes, correct, Noashima. It should be 6. Any is not, don't follow your mathematics because this is filter design. If you have 5.1, when we ask you to order, because order filter is round numbers, so you need to round to the most maximum. If it's 5.1, it should be 6. If it's 5.2, it should be 6. Don't round it like 5.1. Okay, it's 5.1, so it should be 5. No. If it's 5.1, means it's not enough to produce filter response required for order n over 1. It's better to be more, not less. Okay. So example here, been given Butterworth response. Actually, you guys can try, because I already explained in the video how to get this. Saya siap simpan lagi yang saya conteng ni. Okay. You can try first, then you check whether you get the same answer as me and the answer of the solution here. Okay. You need to try, otherwise you didn't know. So you have 0.891. This one is actually the linear scale, and this one is actually the dB scale. Okay. So the first step, calculate the order number. Okay. Here 5.98, so you end up with 6. Okay. This one is Butterworth low pass filter. Okay. And then you sketch the magnitude response of this filter. Saya ada sketch tak? Ke saya malas? Oh, I didn't sketch. But you please sketch, because it's difficult to write on the screen. Okay. Okay. So you need to sketch, then you sketch the, first you determine the order, then you sketch. Sketch is actually for you to locate, okay, for you to locate which one, where is your omega P, where is your omega C. This is omega C. Sorry, please check your own paper. This one is omega C. C dia termasuk kat sini, nampak tak? This, okay, there is a bit error. This is omega C. You can see the C is here now. Salah, silap. Okay, okay, and then you have the flat pass band gain. This is your stop frequency. This one is your stop band gain, and this one is stop pass band gain. Okay, so you need to sketch it so that you know where is it. Okay, and also there is some mark. Don't follow me. I don't do it because the time is night time. I'm sick, so I just focusing on solving until I forget to sketch. Okay. So step 2 is actually you need to determine the omega C. Okay, you need to determine omega C, and then omega C actually you have two kinds of omega C. Like I told you, one is dependent on this alpha P, one is dependent on this your alpha S. Okay, so you have two kinds of omega C. One is 11.18, the other one is 11.27. Okay, then you will calculate what is the alpha S and alpha P. So you see the alpha S here is actually 0.030069, and this one is alpha P like this. So you go back to the specification that required by the question. So you can see this one is 0.03069 is less than 0.0316 required by the specification, and this one is within the range. Okay, within the range. So where is the specification? Okay, a pass band gain between 1 and 0.91, between 0.91. So this one cannot accept for the other WC because it is more than 0.91. Okay, so that's why we cannot accept this. So in this kind of specification, you end up to choose 11.19. Okay, you need to try this. Don't only see like watch cinema, eat popcorn, then okay, I understand. You will not know you understand or not unless you try it yourself. Okay, so this is the step, but you can refer to the video as well. Okay, and the step 3 is actually you determine the normalized transfer function. Okay, Bn here. So normalized transfer function is actually Hn equal to 1 over Bn. 1 over Bn. Then the answer is order filter 6, so you have this. Okay, until F5. So that's why you have S6, S5, 4, 3, 2, 1, and the last will be 1. Okay, so this is your this is your normalized transfer function, which is not the actual transfer function. And after that, because this question is about, we go back what they want. They want a Butterworth low pass filter. Okay, so Butterworth low pass filter. After you obtain the normalized transfer function, you will go to the table 5F.5. Then you need to transform it. To transform it, you need to denormalize it to have the actual transfer function. So you replace S with your S over omega C. I don't know what is this error, but at least you understand. You replace S with S over omega C. So this equation that you have here, all of them should be replaced with S over omega C. Okay, then you expand it. Depend. You want to expand or you want to let it in this term. Okay, depends. Also depends on the question what they want. Okay, so you can if they didn't specify, you can let it like this. It's look simple to the eyes to. Easy for the eyes to read it. Other than you expand it, but if you expand it, it is not wrong either. Okay, so here, so if it's the Chebyshev, you just replace it S over omega P. But this question is about Butterworth. Okay, so okay, this one will be covered in the chapter 6 part 2. Okay, I'm worried that maybe I forget to record, and maybe it's better that I record that, because if I record, maybe you will have much more information. Okay, so I will record this chapter 6 part 2 later on. Okay, it's a bit more complicated for this Chebyshev. Okay, but later on. Okay, so your chapter 6 part 1 is only until Butterworth filter response. Okay. Okay, until before slide 28, which means until slide 27. So what you can do, okay, what you can do, this exercise, go to here, okay, don't wait until the next tutorial because I know you guys busy, right? Many works also. Dah 2 minggu lah batuk saya tak habis lagi, 2 minggu lebih lah. So, okay, wait mana saya nak. Okay, give 2 differences between Butterworth and Chebyshev filter for marks. Okay, this is final lah. And then now you can do this question because this is Butterworth. Okay, obtain the normalized, calculate the cutoff, what will happen. Okay, so do this first. This one is what? In a AM broadcast to prevent interference from other regions, the stop band gain of at least and transition band region. Okay. For the given questions, catch the filter frequency. Okay. Oh, okay. So question 2 is Chebyshev. Good lah. So you do 1 and B first. And when I already produced the chapter 6 part 2, which is Chebyshev, you can do this. You can continue. I don't need to tell you one by one. I think you are adult already. Okay. So when I already provide chapter 6 part 2, you watch. Oh, it's Chebyshev. And then Raimi already give exercise on Chebyshev. So you do. Okay. Okay, with that, we finish this this lecture. I will share the other. I will share the recorded session later on. Make sure you watch the YouTube video. I'm not like promoting my video, but it's for you. I'm worried you didn't watch and you didn't learn. Okay. Okay. Thank you. You may leave. Okay. Have a nice day. Welcome. Welcome.
Thank you, Doctor.
Welcome.
Doktor, saya nak tanya yang buat plot tu kan, kita memang kalau nak plot graph tu nanti kena buat putus-putus ke
tak
boleh
kisah.
buat straight
Yang
line
penting
je?
dapat beza.
Oh, faham.
Yang penting dapat beza the main line, yang maksudnya line yang resulted tu kan. Jangan buat dia macam nampak hampir sama dengan yang line yang individu tu, sebab at the end we want to see the line tu, the main line tu.
Oh, faham.
Doktor siapa? Balkis siapa ni? Next sem EMT ajar section. Okay. Balkis mana ni? Saya malas nak type penat. Balkis gimana?
Saya.
Next sem saya ajar EMT. Dengar cerita saya memang ajar EMT next semester because from our school. Sekejap saya tutup record ni sekejap. Dah tak boleh benda ni dah. Sekejap Sekejap stop.